Amazing. Okay. Hello, everybody, and welcome to Women in Rust Lunch and Learn. My name is Lizzie Holmes. I'm the head of operations here at SurrealDB, and I'm joined by Dr. Caroline Morton. Caroline, you haven't added a doctor into your name. Software developer, epidemiologist, and senior clinical research fellow here at Surreal. We co-launched Women in Rust back in April. I'm super excited to say it's now grown to 175 members, which is really exciting. And of course, a warmer welcome to all of the wider community who is going to be watching this. Due to popular demand, we are going to be sharing these recordings on YouTube for everybody to access. We're really, really excited today to be joined by Gabriella Burns, Associate Software Engineer at Moody's Analytics. Gabriella actually joined us in person for our first live Women in Rust back a few months ago. So we're really happy to now have her leading our 4-part series of exploring Rust API use cases. Gabriella, welcome.
Thank you so much, Lizzie. I just want to say that this community has been so special. I mean, I love to see how quickly it's grown, and I really appreciate everyone being here today. So today's Lunch and Learn is going to be focused on exploring Rust API use cases through the lens of performance, safety, and scalability. Again, my name is Gabriella Burns, and I'm a software engineer at Moody's. So I am a self-taught software engineer, and I work in know your customer and anti-money laundering technology. Philippa, like you, I'm also in the financial space, and I wanted to move into software engineering. Although I really did not plan this. If you told me 5 years ago that I would be up here talking to you about Rust, I mean, I wouldn't have even known what Rust was. I studied public health and environmental studies at Tulane University, then moved into working in documentary filmmaking, and then got a job at the Department of Health in New York City over COVID. And then I landed myself at Moody's, working as a data specialist. And I was working in a product that specialized in sanctions, financial crime, and adverse media data, which was really interesting. It was such a great lens to view the political landscape through. The work was interesting, but there were parts of the job that I didn't love, mostly making Excel spreadsheets. And so I took a data analytics course to try and help with that. And then I encountered Python for the first time, and everything just sort of clicked. I realized that there are tasks that I didn't love doing that I could automate through Python. And so I realized I really loved coding, and pursued a position within the company on the software engineering side of things. So 2 years and 3 laptop upgrades later, I've made the transition in. And Rust has been a big part of that. It was the first language I learned other than Python. And I asked to be thrown into the deep end of Rust. So the first task I was given was building some API endpoints. Those endpoints were just the start of this journey. So I have developed this workshop series. This is, if you don't know, the first of 4 in partnership with Women in Rust. And that's been based on my experience with Rust and API development best practices. So a little bit about the work I'm doing now. My current team is called App Store. So we build APIs and features that enable third parties and internal data providers to integrate with our platform. So that's a little bit about me and why I'm talking to you today. So the obvious first question is, why build APIs in Rust? There are a few reasons. One of the big ones is the ownership system and strict compile time checks. These help prevent common programming errors like null or dangling pointer references, buffer overflows, and data races. This leads to more stable and secure APIs. Another reason is the growing ecosystem of Rust. The web frameworks and the libraries that facilitate API development, and the people who are behind building the language in general. So I thought that I would turn to a few members of the community to see why their company was using Rust for API development. So you don't just get my perspective. And Alex Payne, a senior software engineer at Esri, was kind enough to send in this quote. So big shout out to Alex. If you don't know, Esri is a GIS software, and it is really interesting. I used it a lot at school. I love making maps with it. It's great. So he said, our services need to work with complex data structures. They need to be fast and stable, and they need to be prototyped and iterated on quickly. We found that Rust satisfies all of those needs. Strong typing significantly simplifies working with complex data structures. Its runtime performance and compile time borrow checker helps ensure that we have a fast and stable product the first time around. And we found that the ecosystem has high-quality web frameworks available for our API development, which has enabled us to quickly iterate on our API designs and share them with customers in a timely manner. Thanks again, Alex, for that. And I wanted to, before we dive into the technical reasons that we write in Rust, I wanted to talk about the people a little bit more. So Rust has maintained its status as the most loved language by developers for the 7th year running in Stack Overflow's annual developer survey. And people who write in the language that they enjoy writing in are happier at work. I think that's a huge thing to point out. But one aspect of the people writing in Rust that is not as great is that only 3% of Rust engineers are women. And if you're in this room today, I think you'd agree that it's time to do something to change that. So I'm just going to go over a little bit of terminology before we got started. So we're going to talk about memory safety so much you'll be sick of it. It's a property that prevents unauthorized access or corruption of memory, eliminating issues like buffer overflows and use after free errors. Then we have explicit error handling. This is an approach requiring developers to explicitly manage potential errors, ensuring that all failure scenarios are considered and handled in the code. Finally, let's talk about strong typing. That's strict enforcement of variable types, restricting operations between different types and catching type-related errors at compile time. Like I said, you're going to hear so much about memory safety, you'll be sick of it. So first, let's cover it from the standpoint of security and reliability. So Rust's memory safety guarantees help to prevent common issues. I think I've said buffer overflows and null pointer dereferences already, and use after free errors. So this leads to more secure and stable APIs. Memory safety issues account for a significant portion of security vulnerabilities in large software projects, and they're effectively eliminated by Rust's design, which significantly improves API security. And security is really the name of the game, especially if you're in a space like financial technology. It's important to keep that data safe. So then there's a focus on unsafe code. When it's necessary, Rust clearly marks it, making it easier for reviewers and static analysis tools to focus on potentially problematic areas of the API. Finally, we have concurrent programming safety. Rust's ownership system and borrow checker ensures thread safety, which makes it easier to build scalable concurrent APIs without data races. Now let's look at memory safety from the perspective of development efficiency and performance. So Rust offers a unique combination of development efficiency and high performance, and that makes it ideal for creating scalable and maintainable APIs. So it has compile time guarantees. The ownership, borrowing, and lifetime rules ensure memory safety at compile time, so those potential runtime errors are caught early. And that kind of leads us into the reduced debugging time. By catching memory-related issues at compile time, Rust can significantly reduce the time spent debugging memory problems in API implementations. Finally, we have maintenance and refactoring. The strong type system and memory safety guarantees make it easier to refactor and maintain APIs over time, as many potential issues are caught once again at compile time. If you're just getting into Rust now, remember the compiler is your friend no matter how angry it makes you. It's like the friend that's telling you what you don't want to, we don't really want to hear, but what you need to hear. So let's move on to explicit error handling. Rust's result type forces API designers to explicitly specify what errors a function can return. This creates a clear contract between the API and its users about possible failure modes. The ergonomics of Rust are really important. While explicit, Rust's error handling is designed to be ergonomic with features like the question mark operator and the from trait for error conversion. Then there's the compile time error checking. The compiler ensures that all potential errors are handled, which prevents runtime surprises, and nobody likes a runtime surprise. So this leads to more robust APIs. Finally, we have the reliability. By forcing error handling to be explicit, Rust APIs tend to be more reliable and have fewer unhandled edge cases. So this leads to more predictable and stable software. Okay, so why is strong typing a benefit in building Rust APIs? The type system allows developers to define precise contracts for API inputs and outputs. This makes it easier for API consumers to understand how to use the API correctly, and it reduces the likelihood of runtime errors. So we'll look at this again from a refactoring and maintenance perspective. So it makes it easier to refactor code and maintain APIs over time. This is partially because changes that break the API contract are often caught at compile time. Remember, the compiler is your friend. Then we have concurrent programming safety. Rust's type system, combined with its ownership model, helps to prevent data races and other concurrency issues, which is crucial for building scalable APIs. And there are the performance optimizations that come from strong typing. The compiler can use type information to make optimization decisions. That can lead to faster API execution. So those checks that would be performed at runtime in a dynamically typed language can be done at compile time in Rust. Okay, so I'm going to go through performance, safety, and scalability now, and we will take a look at a couple case studies. relating to this. So why is Rust good for API performance? Zero-cost abstractions are one of the primary ways it accomplishes its goals of safety and speed. The ownership system is a good example of why this works. Rust variable bindings have ownership over what they're bound to. So when a binding goes out of scope, Rust frees up the bound resources. So Rust design ensures that high-level abstractions have zero runtime cost. So you get the performance of low-level code without sacrificing safety or reliability. Now let's talk a little bit about low latency execution. Rust's ability to compile directly to machine code results in highly optimized binaries that execute with minimal latency, and this makes it ideal for performance-critical applications. Then there's the efficient resource management of Rust. Its ownership and borrowing system allows for precise control over memory allocation and deallocation. And this eliminates the need for garbage collection, and it reduces runtime overhead. Then there's compile time optimizations. Because Rust performs many checks at compile time rather than runtime, that reduces the need for runtime checks, and it improves execution speed. So we'll get a little bit more into performance. Concurrency without data races is very important. So Rust borrow checker ensures thread safety, and that allows for efficient multi-threaded execution without the risk of data races. Then there's a high throughput. Rust APIs can handle a high number of requests per second, and that makes them suitable for high traffic applications. And because Rust catches many errors at compile time, it significantly reduces the amount of time spent on debugging and allows developers to focus on optimizing performance instead of fixing some annoying bug. Okay, let's move on to the case study of Discord. So in case you don't know what Discord is, it's a popular communication platform that serves millions of users worldwide with a variety of communication services. And the platform grew rapidly, so maintaining performance for real-time features became crucial for user experience. So some of the problems they experienced were latency spikes. Their read state service, which is critical for tracking user message interactions, experienced latency spikes. Then there's the garbage collection overhead. So they were previously written in Go, and the garbage collector caused periodic performance issues despite extensive optimizations. And finally, we have scalability. The growing user base demanded a more efficient solution to handle millions of concurrent users and billions of messages. So Discord solved this by adopting Rust to address performance challenges in their backend services. The async await syntax and ownership model enabled efficient handling of async tasks and high concurrent users. So then by eliminating the garbage collector related latency spikes by switching from Go to Rust, they're able to provide more predictable performance. And Discord actually has some publicly available data on this. So they were able to handle a significantly higher number of concurrent users and messages. And that ensured the responsive user experience even as the platform grew rapidly. So how much did the performance improve? their Rust version used 30% less CPU, 90% less memory, and they achieved a 10 times reduction in latency. It's important to note here that their Go version was highly tuned, and this was their newer Rust version, so I'm sure they iterated on it from there, but those numbers are staggering. And I think it's a really good example of why companies are making the decision to switch from languages like Go into Rust. Okay, so let's talk a little bit more about safety. And then we'll go into a case study with Cloudflare. So memory safety and REST APIs is, of course, very important. I told you from the start I was going to talk a lot about this. So the ownership model is a key piece of this. Rust's ownership model ensures that every piece of data has a single owner, and that prevents issues like double free and dangling pointers. The borrow checker enforces rules on how data can be accessed, and that ensures that references are always valid and prevents data races in concurrent contexts. And there are no null pointers. So Rust eliminates null pointers by using the option type. And this ensures that all possible states are handled explicitly. Then there's safe concurrency. So Rust's strict rules around mutable and immutable references ensure that concurrent code is free from data races. Let's look at safety from a security and reliability standpoint. So Rust's memory safety guarantee prevents common vulnerabilities like buffer overflows, use after free errors, and null pointer dereferences. It essentially eliminates entire classes of bugs. And then there's explicit error handling, like we discussed before. So the result and option types enforce explicit error handling, and that makes APIs more robust and easier to use correctly. Finally, let's bring it back to the focus on unsafe code. When unsafe code is necessary, it's clearly marked, and reviewers can focus on potentially problematic areas, like really pinpoint it. Okay. Now we can move on to our case study of Cloudflare. So Cloudflare is a leading internet security and performance company that provides a wide range of services. This includes content delivery networks, DDoS mitigation, and edge computing solutions. So as their services grew in scale and complexity, Cloudflare faced increasing demands on their infrastructure and API development processes. And security is one of the problems they faced. As a security-focused company, Cloudflare required robust safeguards against memory-related vulnerabilities and other common security issues. So their solution here, you guessed it, includes the adoption of Rust for critical infrastructure and API development. So that's enabled them to build more robust, efficient, and secure systems. So rewriting their protocol implementation in Rust. Then they also use Rust for firewall rules, for their firewall rules engine, which processes millions of requests a second. Really high traffic. Wow. Okay, so let's talk a little bit about scalability. So scalability features and Rust APIs. Let's start with efficient concurrency. So this Rust API, Rust async await syntax, and zero cost abstractions allow for efficient handling of concurrent operations, which is crucial for managing multiple client requests simultaneously. Async runtime is another key factor here. So libraries like Tokyo and Async STD provide robust support for async programming, and that enables scalable API development. The low resource usage is also a key factor here. The efficient memory management and lack of garbage collection result in APIs with low memory and CPU usage. That makes them scalable under a high load. And then there's the fine-grained control that developers have over REST APIs. So you have precise control over system resources and can optimize them for handling async requests. Then there is the high throughput aspect. REST APIs can handle a large number of concurrent requests, and that makes them suitable for high traffic applications. The dynamic scaling is also important here. So Rust's efficient concurrency model allows APIs to scale dynamically with the number of incoming requests, maintaining performance under varying loads. I know this is really important for my work. There are times when clients send really large and complex profiles through, and we have to be able to scale accordingly. Then there is the community and ecosystem of Rust. The growing ecosystem of Rust libraries and frameworks like Actix Web, Rocket, and Warp support scalable API development. And so we are going to look at a little case study on Figma now relating to scalability. So Figma is a leading design and collaboration tool that enables teams to work together in real time to design projects. It facilitates work between designers and engineers, which allows programmers to understand what the end result of their work should look like. I don't know how I would function without Figma. It's really key for interacting with our UX teams. So it's no surprise that the company grew so quickly. But as Figma's user base grew, the need for scalable and efficient backend became critical to handle that increasing load and ensure seamless user experience. If you're a design platform, then it has to look good at all times. So their solution was to rewrite their multiplayer server, and that is what handles real-time collaboration in Rust. The transition resulted in improved performance and scalability, allowing more users to collaborate simultaneously without performance degradation. So the efficient use of system resources with Rust has allowed Figma to support a growing user base without a proportional increase in infrastructure costs. So now we are going to talk a little bit more about the companies who are adopting Rust or making it easier for developers to interact with their APIs in Rust. So let's start with AWS. They use Rust in several of their services, including Amazon S3, EC2, CloudFront, and Route 53. And let's move on to Google. So they have an official GitHub repository for Google Cloud Rust client libraries. While experimental, it is supported on a best effort basis and allows community contributions. I'd also just like to point out that Google's built a comprehensive Rust course. So it's designed for engineers who are comfortable in other languages but want to learn Rust. And I've used it as a resource for self-teaching myself. It's not really designed to work like that. It's supposed to run in a workshop format, but I found their repos really helpful as I've continued on my journey of learning Rust. And then there's, we'll finish off the tech giant section with Microsoft. So they released Rust for Windows, which provides a way for Rust developers to call Windows APIs. And this includes support for several of their APIs. Okay. So there are also some really interesting technology and internet services companies who are using Rust. If you know Node, you know NPM Inc. The company behind the Node.js package manager has implemented parts of their service in Rust to help them achieve better scalability and efficiency. And there's Mozilla, who is the original creator of Rust. And they use Rust in multiple projects, including parts of the Firefox browser. And then finally, our wonderful hosts today, SurrealDB, they rewrote entirely from Go to Rust. They have a few reasons for this. So, of course, Rust provides better control over system resources. The memory safety offered by Rust borrow checker and lifetime system was also a big part of their decision to make the switch. And then there are the benefits of Rust's ownership model and thread safety. This helps write better concurrent code. Then the advanced type system and pattern matching in Rust was really important to them. And then there's the rapid adoption of Rust. Like I said, it's the people, it's the ecosystem that also makes it so important. It goes beyond the technical aspects of the language. Rust is being adopted rapidly, and it's seen as the future of systems programming. So it makes sense that SurrealDB would want to move towards it. And of course, I think you should always talk to what you know. So I've included a little case study on Moody's and the work I've been doing there. So Moody's was traditionally a ratings business, but it acquired several companies to form its analytics arm a few years ago, and that included Passport, which is a software as a service workflow platform for identity verification, customer onboarding, and risk analysis. So that is the part of the platform I work on now. And its advanced automation, integration capabilities, and comprehensive compliance management features made it a valuable addition to Moody's tech stack. And Rust APIs are an integral part of our code base, especially when interacting with data providers. And then, of course, we'll go through why we've done it from a safety, performance, and scalability perspective. So Rust's ownership model and strict compiler checks help to prevent common programming errors. That's important for making more robust and secure APIs that can handle customer requests reliably. From a performance perspective, Rust's low-level control and lack of garbage collection result in higher performance. And that allows APIs to handle a large number of requests quickly. Finally, there's the scalability. So the async runtime like Tokyo is designed to scale well. And this allows APIs to handle increasing numbers of concurrent requests efficiently. Yeah, and we have a few more reasons we use it. There's the fine-grained control that our developers are able to use to our advantage. It gives us precise control over system resources, and that can be optimized for handling async requests. And the customizable concurrency is great. It allows developers to easily control the number of worker threads or the equivalent in async contexts, and that allows for fine-tuning of request handling. Then we have the low resource usage. Rust programs typically have a low memory footprint and CPU usage, and that's beneficial for server-side applications that are handling many requests. And then there's the efficient concurrency. Rust async and await syntax and zero cost abstractions. I mean, I've probably said that about 10 times now, but it's so important for handling a high number of concurrent operations efficiently, which is crucial for managing multiple client requests simultaneously. Yeah, so this is what I've had prepared for you today. I hope it's been useful. I hope it's been a way to encourage you on your Rust journey. And before we get into questions, I just want to say that I am really excited to be leading some in-person workshops coming up in September with the Women in Rust group. So we will put out some more information about that, but I hope to see some of you there. Yeah, I'm really looking forward to it.